So far, all the GAMs we have seen have been univariate. They have a single predictor for the outcome. However, we can perform multiple regression with GAMs. Multiple GAMs also can contain a mixture of smooths, linear effects, and continuous or categorical variables. In this lesson, we'll learn how to use this flexibility to fit a variety of different models to data. We'll now work with the MPG dataset. This is a dataset of 205 models of cars consisting of various traits like their make, model, cylinders, price, and weight, and their city and highway fuel efficiency. We'll be building models that use the vehicle traits to predict fuel efficiency. Let's start with a very simple one-variable model. Here's the code for a model that predicts highway fuel efficiency as a smooth function of automobile weight. The resulting model captures the nonlinear decreasing relationship between these two variables. To add an additional variable, such as length, we just include another s function in our formula, separated by a plus sign. Here, we add car length as another predictor. We see from these plots that length has an increasing nonlinear effect on fuel economy, and this effect is weaker than the weight effect. Note that in this model, both the effect of weight and price are nonlinear terms, but the two are simply added together to get a final prediction. That addition is where the additive in generalized additive models comes from. Not every term in a GAM has to be nonlinear. You can combine linear and nonlinear terms. To add a linear term, don't wrap the predictor in the s function. Here, I've made the length term from the previous model linear. In practice, we rarely make continuous variables linear in GAMs. This is because if a relationship is really linear, or there is not enough data to show otherwise, automatic smoothing will force a linear shape. We can produce the same model if we set the smoothing parameter of the length term very high. Strong smoothing results in a linear model. However, linear terms are very useful when we have categorical variables as predictors. For instance, in our MPG dataset, the fuel variable has two categories, diesel and gas. When we include a linear term with this categorical variable, the GAM function fits a model with a fixed effect for each level of the category. Here, you can see that having gasoline has a negative effect. Diesel vehicles are more fuel efficient. In this model, the nonlinear effect of weight applies to vehicles of both gas types. This is the nonlinear equivalent of the fixed slope, varying intercept models you may recall from a linear regression course. Note that when you use categorical variables this way, it's important that the variables are stored as factors. The MGCV package does not use character variables. We can also specify a GAM formula that will fit different smooths for different categorical variables. We call this a factor-smooth interaction. By specifying the by argument in the s function, we can tell R to calculate a different smooth for each unique category. You can see here we have different smooths for diesel and gas cars, but the diesel smooth is much more uncertain. Usually, when we have smooth factor interactions, we also include a varying intercept in case the different categories are different in overall means in addition to the shape of the smooths. Here, you see adding this varying intercept improves the estimate of the smooth for diesel cars. Now, let's practice fitting these different combinations of models.